And lastly, we have a combination. So you almost always hear these two concepts together. And because they are similar, but there is some requirement to make them different. So for the combination, we still counting things, but there's different requirements. So let's take a look at the definition first. The combinations are the possible selections of items from a group of n items, regardless of the order of selection. Okay, that's several things to digest. Okay, so here we have a group of n items. So we still have, because you can still think of them as balls of with numbers from 1 to n. Now we still select our items. We want our items. Maybe you select 2, you select 1, you select 3, you select 5. But we don't care about the order, regardless of the order. What it means by that? It means you can think of selecting things and just put them in a box and check them. If you check them, then that means you don't care about the content of the box. Also, if you have like 2 boxes, one has the ball number 1 and 2, the other one has the ball number 2 and 1. If I ask you, are they the same box? Then yeah, they are the same box. They have the same contents, like 2 balls with 2 labels. They are just in different positions. And so that's one way to think about a combination. Put them all in a box or in a bag. Another way is if you think about like cards in your hand. You have cards and you shuffle them. That means you don't care about the order of the cards. Or like when you play card games, usually you don't care which one is the first one you draw, right? Once you have cards in your hand, you can play any cards you want. So that's another way to think about combination. And formally we can think of them as sets, which is more abstract, but is it kind of needed? If you remember the set notation, like the set with 1 and 2 is the same as the set with 2 and 1. When we have sets, we don't care about the number, which one is first, which one is second. Like all we care about is it's this kind of abstract idea where there are some elements inside, and you don't care about where it is inside. Is it on top, bottom, left, right, back, front? And they're the same. If you express them as a Venn diagram or an Euler diagram, they are the same anyway. So that's the combination. And so let's see if we can list combinations. So how many combinations are there of 2 letters from 3 letters? So in this case, how many items we have in total? We have 3 items. So n is 3. How many letters we choose or select? Only 2. So we choose 2 items out of these 3 items. So if you plug into the formula, then that's first you would them into. But then how do you express all the combinations? The problem is if you just write this, if you use the same notation, then you could treat it as a sequence of letters. So it will be different in terms of letters, but it will be the same in terms of combinations. AB and BA are the same for combination. So that's a problem if you cannot use the same notation anymore. So I kind of suggest that you use a set notation, because again, once you have the set notation, then these 2 sets would be the same, and we don't double count. Okay, let's use a set notation to make it more clear. If there are 3 letters and you have to choose 2, then what are the possible combinations? You can choose A and B. You can choose B and C. You can choose A and C. And that should be it. That's pretty much it. So that means there are 3 combinations. As simple as that. And yeah, you might ask, what about B and A? Oh, we already count that. No, these two sets are the same. What about C and B? A is there. We already count B and C. What about C and A? Yeah, we already count A and C. And so in a sense, like a you can get combinations from permutations. If you go back and list all the permutations, right, then you can pair up or cross out the ones that have the same combinations. So A and B and A are the same combinations. AC and CA are the same combinations, and B and C and B are the same in terms of combinations. So we are left with just 3 combinations out of these 6 permutations. So that's one short example for counting combinations by hand. And also notice that you can't use the tree diagram anymore. That's a big warning. You can try, but it's not going to give you the result you have. Like for instance, if you try this tree diagram, it kind of works at first. You choose A, and then you can choose B, and then you can choose C. Then yeah, that kind of works. But here, if you choose B first, then you cannot choose A anymore. But that's gonna give you the same combination as the first one. And so BA doesn't work. Like B needs to be paired with C then. We haven't choose C yet. So there is only one leaf for this branch, but 2 leaves for the first branch. And this is why the rule of product fails. And also for C, usually you could choose A or B, but they both fail. Like CA is already in the first branch, CB is already in the second branch. So in fact, you cannot even choose C in the first place. C has been chosen already somewhere earlier. And so this tree diagram breaks apart. And you have to choose some other method. That's how you make a combination of 2 letters, of 3 letters. Let's try another one. Yeah, this is more difficult because now there are 5 letters and you are asked to find combinations of 3 letters. This is more difficult if you are not careful. Let's see, you can choose A, B, C, that's given. If you fix A and B, then we can change C to D, and we can change C to E. Now we have these 3 combinations with A and B. What about A and C? If you choose A and C, what can be filled as the last one? Then you can't fill B anymore. Right? That was the first one. So C, B doesn't work. You have to start from D, right, and then E. Okay, so that's all the combinations with A and C. And lastly, if you choose A and D, the last one must be E. If you choose B or C, then it must be somewhere earlier. Okay, so now we have 6 permutations with A and something else. And then we have to choose B and C. And we cannot choose A anymore because it seems that we have all the A's. We have to choose B and C and then D maybe? And then B, C, and then E maybe? And then you can see that it is easy to miss some of the letters in C, D, E. But if you are careful enough, this should be all the combinations you can get from these 5 letters. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 combinations. Right? Right? Yeah, hard to tell. You have to be pretty careful to not repeat things. So this is where we start to, look for formulas. Because otherwise it's gonna take forever to compute all these things. And so, yeah, luckily we have a formula. Like the formula is oh, I forgot to mention, like earlier we have a formula for permutation. We have a letter P, so P is for permutation. Similarly, the formula for combination has a letter C. And we have and there are two parameters, there are two variables, n and r. The number of objects in total and the number of objects we choose. In this case, we have C and R. And the formula is n factorial divided by r factorial times n minus r factorial. So for now, the formula doesn't make sense yet. And maybe I'm sure you have used this before and it still doesn't make sense. Right, but if you have enough time, then this can actually be proved in two ways. But yeah, let's assume that you believe me that this formula works. And we're gonna use it later. And this formula is used a lot, right? It's used a lot, and it is used in different branches. It is used in math, computer science, used in biologies. The people use them everywhere. And so that you might see this in different notations. The one we use in class is C and R. And to give you a sense of, okay, it is a function. There are two variables, there are two numbers you have to plug in. So that's what we use here. But the abbreviation is as follows. So you draw a parenthesis. We have n at the top, we have r at the bottom. You don't put that line between those two numbers, like, because this is not a fraction. This is just a new notation, and choose C and R. So please refrain yourself from putting anything between these two numbers. So that's a slightly abbreviated formula. Oh, and also sometimes in some textbook you will see this C and then N and R. And sometimes you see like C and R. These are wild. People use lots of various variations of these formulas. So, but yeah, make sure that you understand the concept of, yeah, there are n objects, you choose R, and no matter where they are, like they all have the same commutation, they all have the same formula. So let's go to how we can apply that. So let's go back up here, like for the first two. Like for instance, for example 9, if you want to compute the number of combinations, like you would plug in the value 3 and 2. There are 3 letters to choose from, so n is 3, and we choose 2 at a time, so r is 2. And the formula says we need n factorial divided by r factorial times n minus r factorial. And if you compute that, you should get, oops, if you do that, then you should get, okay, sorry, there it is. Right, n is 3, so it's 3 factorial. R is 2 factorial. And then n minus r is 3 minus 1. Oh, sorry, 3 minus 2 factorial. I was ahead of myself. 3 factorial is 6. 2 factorial is 2. 3 minus 1 is 3 minus 2 is 1. 1 factorial is 1. So it's 6 divided by 2, which is 3. So hopefully it's the same as the number that we just got above. And yeah, we did get 3 combinations. What about the next one? The next one, there are 5 letters. We choose 3. So this needs the formula C and R. In this case, n is 5 and r is 3. Okay, there are 5 numbers to choose from, and we choose 3 of them. So it's C5 3. So it is 5 factorial divided by 3 factorials times 5 minus 3 factorial outside that. It should give you 5 factorial is 120. 3 factorial is 6. 5 minus 3 is 2. 2 factorial is 2. So it's 120 divided by 6 times 2, which is 12. 120 over 12 is 10. But that's the answer for example 10, which hopefully that it's the same as the number we got earlier. And so that's how you use a formula for combination. And let's see where I can go. Yeah, let's see the last example here. So back to poker. All the poker face hands can be computed using permutation and combination. So the question is, how many different flush hands are there? Again, in the standard 5-card poker. So the flush is a hand of cards where they all have the same suit. Let's say heart. But the number, the face can be anything. But of course they have to be different. If some of them match, then that means you take a card from different deck. And you will be cheating in poker. That works in blackjack. If you play blackjack, you might see 2 cards of the same face and suit, but not in poker. Okay, so the question is asking how many flush are there. And in this question, you kind of need a mix of rule of product, some permutation, combination. Let's see which one you need to apply. So here we need the rule of product, right? Because to get a flush, we say that it can be of any suit, but which suit? And that means we have to perform this in 2 different steps. Step 1, choose a suit. Because actually the suits are equivalent. You can choose a spade, you can choose a heart, you can choose a diamond, you can choose a club. They all work. So there are 4 ways you can choose a suit. And then in step 2, so you have to choose 5 faces. So you should say 5 different faces. So for instance, you can choose 2, 3, 10, Jack, and 5. The question you ask before you compute the formula is that, does the order matter? And does it matter if you get 2 before 3, or 3 before 10, or Jack before 2? The answer is no. It doesn't matter. And once you have every card in your hand, then they all form a single hand. You don't get more money, or you don't get more prize. No, for have them in order from smallest to largest. We don't care about the order. And since the order doesn't matter, then that means we are dealing with the combination. Just want 5 different numbers, 5 different faces. So we choose 5 faces. From how many faces? From 13 faces. So in step 2, there are 13 faces to choose from. So it's from 1, which is 8, 1, 2, 3, 4, 5, up to 10, and then 3 more, Jack, Queen, King. So 13 options. And R is 5. We need 5 of them. We need 5 different cards. So in step 2, the number of ways are C, 13, and 5. So this is where we use a combination. And the answer is simply the product of these 2. And so it is 4 times C, 13, 5. That's the answer. But in case if you want the number, then you can do that. Like 4 is 4. 13, C, 13, 5. You can use a calculator, which is better. Right? But in case if you want the formula, then it is 13 factorial divided by 5 factorial. That's n, the larger one, that's r. And then the difference, 13 minus 5 factorial. And if you do the math, then the answer should be 4 times 1287. which is what? 5,148. So that means there are 5,000 ways to get a flush. And so that's the answer for this example. And just a quick note here, if you remember earlier we talked about 4 of a kind. 4 of a kind. And do you remember how many 4 of a kinds are there? I think it's 13 times 48, which is in the 624, I think. So that means there are a lot more flush hands than 4 of a kind. And that's why 4 of a kind is ranked higher than the flush. And so that's the end of the combination.